Thank you very much, and thanks Dennis and Osvaldo for the invitation. Very nice to be here. So I'm going to make a swift switch of the topic from learning to not learning. Namely, we want to keep things private, so we don't want to learn. Okay, this is a joint work with Lukas Holzbauer from TU Munich and Ragnar Frey Hollanti from Aalto. Okay, first I'll quickly walk you through private information retrieval and explain what I mean by that. Then we define the PIR capacity and present some conjectures. Then we move on to proving those conjectures, or I won't be presenting any proofs here, but there's our recent ITW submission is available on arXiv if anybody gets interested in the more technical part of the paper. And one of the key notions in this talk is this strongly linear PIR, which I will define and also somehow try to demonstrate that it's an important practical feature of PIR. So recently we have had a lot of interest for private information retrieval from coded storage. So PIR was kind of a hot topic from, let's say, 95 to 2005, but then it was more or less dropped because of impracticality, I guess. So then people were retrieving 1 bit from a database, so forth. But now we are, of course, talking about more of media files, huge files that we want to retrieve, potentially. And so what is the privacy part here is the identity of the file. So the user is known, so there's no anonymity. The files are public, so there's no encryption or security in that sense. But what we want to keep secret is the identity of the file that I want to retrieve. So I want to get something from the cloud, let's say, but I don't want the cloud owner or the servers to know which file I was after. So that's my basic problem here. And there's been a lot of capacity results, for instance, for replicated and MDS-coded storage, colluding servers, where the servers may exchange their queries, single server PIR with site information, and symmetric PIR. And by symmetric, what we mean here is that so the user wants to keep the identity of the desired file secret, but then in the symmetric case, the user also doesn't learn anything extra. So she gets exactly the file she wants and learns absolutely nothing about the other files. And it's been also shown that this MDS, maximum distance separable property, is not necessary to achieve this MDS PIR capacity. And so what we did is to try to close some of the gaps in these capacity results. So not everything is known yet. And so first what we did was this symmetric PIR capacity, this all over the place case, where we have colluding servers, Byzantine servers, stragglers, everything possible. And this is basically just a very straightforward combination of the previous results. And then what is maybe a little bit more interesting is this strongly linear PIR. And I will define later more rigorously what I mean by it, but basically it means that in addition, so usually in linear PIR, we assume that the responses from the servers are linear, so they are just inner products between the queries and the data held at the servers. And in strongly linear, we add the assumption of linear interference cancellation. So basically, when the user is decoding the file from the responses, that process is also linear in this strongly linear case. And so by doing this, we prove the capacity of strongly linear PIR for any number of files. And then by doing this, we also get a proof for a couple of conjectures concerning some asymptotic capacities. Okay, and just to start out simply, so we know that if the data is stored on only one server, then the only thing to get information theoretic privacy is to download the entire database. And this is, of course, highly infeasible, now that we can assume that we have thousands or even millions of files. So to that end, we want to either replicate or do some more elaborate coding on several servers instead. And I'll denote by, my M files by x1 to xm, so it's not powers of x, it's just the superscript indicating the file. And then subscripts for fragments, so if you are doing coding, we usually split the files in pieces and encode to more pieces. So for instance, if we use the 3-2 simple parity check code, I split my file xi into 2 pieces, xi1, xi2, and then I'm just adding the parity symbol to those when I'm encoding. And what we do for storage is that then we take this each file yi and we store the first coordinate on the first server, second on the second server, and so forth. And just a more pictorial example. So assume I have 3 files, x1, x2, x3, and I split them all in 2 pieces. I'm using the 3.2 simple parity check code from the previous slide. And assume the user wants the first file. So how do we do this private information retrieval? So first we choose a random vector, the length of which is the number of files, kind of indicating what I want the servers to do for me. So I'm going to send this random vector plus E1, which is the first standard basis vector, indicating that I want the first file, to the first server, and the plain random vector for the other 2 servers. So E1 is basically just 1, 0, 0. So what it means is that I'm flipping the first bit from this vector U when I add E1 to it. And the servers will compute inner products with my query and their contents. So basically just project their data on my query. And then how I get my response on my file that I want, which is now x1. So I get the first piece x11 by just simply adding up all these responses if I'm in the binary case. Otherwise, I need to do some subtracting. And why does this happen so nicely is this addition of E1, so that kind of helps me to cancel out everything but the first file that I want. And why is this private is that if the servers don't talk to each other, they don't collude, then U is a random vector and U plus E1 is equally much a random vector. So they cover the whole space. And so now I just got the first piece, I need still the second piece. I do exactly the same. I choose a new random vector, and I add E1 to it, but now I send that indicated vector to the second server who is holding the second piece of the first file that I'm still missing. And again, the servers do exactly the same, so they project their data on my query, and then I can compute my second piece of the first file by, again, just adding up the responses. If you look at the red numbers there and add up, then you're left with x12, which is the second piece of the first file. Everything else cancels out. And this is what I mean by interference cancellation, is that I choose my random vectors such that when I'm computing something with the responses, I'm left with the interesting part of the story. Okay, and so in the previous example, I assumed that the servers don't collude, but what if they do? So first of all, what we mean by that is that they may exchange their queries in order to reveal the file identity. And we say that a scheme protects against colluding set J, which is a subset of these n servers, if we have a probability distribution such that if we project the whole space of queries to this colluding set, they see, for instance, the uniform distribution. So they see the whole space. So they can't infer any data from the queries they see, even if they exchange the queries. And we call a TPIR scheme such a scheme that can protect against any T servers colluding. Okay, and then we get to the capacity part. So we define the rate of such a retrieval process as a ratio of the size of the file that I want over the size of the total download I need to do to get this file. So if I have no privacy requirement, this rate would be 1 because I just simply download my file. And we call the capacity, as usual, the maximum possible rate that I can have for a given model. And asymptotically capacity achieving if my rate is the limit of the capacity as the number of files m goes to infinity. And just to give a very quick example, so Sun and Jafar proved this capacity of replicated PIR on n servers with m files. And this is the capacity expression. And as usual, you have a converse, which is some information theoretic bound for what the rate can be at most. And then you design an achievable scheme that can get to this rate. And I won't show the converse. I assume you are all familiar with information theory and can imagine how that would go. But just to demonstrate the achievable scheme, I give a really small example. So 2 files, A and B, stored on 2 servers via replication. And I split both of the files into 4 simples. And what I do is my query strategy is as follows. So first I download A1 from the first server, or my query relates to downloading A1 from the first server. And because of privacy or symmetry, I need to also download something about the file A from the second server. And because I don't want to reveal that I want the file A, I need to also download pieces of the other file. And then I need to be able to get what I want, so I need some kind of parity symbols as interference to be able to cancel out the crap. And then I use these to get what I want. And then, of course, finally, I need to symmetrize again. And I don't want to do it in such a systematic manner, but I want to permute my indices to make it more random. And this gives us a rate 2/3, which matches the capacity expression on the previous slide. And now if you look at this a bit, you maybe notice that the splitting of the symbols is actually n to the m. So it's exponential in the number of files, and the files can be very many. So this is not the feasible scheme in practice, I would like to say, but it's nice for demonstrating the capacity. And okay, so what are the conjectures that we are going to prove? So maybe slightly boringly, these are our own conjectures. Usually it's more fun to prove other people's conjectures, but anyway. We were claiming or conjecturing in our previous paper, which just came out on TIT, that the asymptotic capacity as the number of files goes to infinity from an NK MDS coded storage with T collusion, P Byzantine servers, R unresponsive servers is as there. And then the other conjecture looks exactly the same, except that it says SPIR, which is the symmetric version of the problem. So these capacities coincide according to our conjectures. And then there's an earlier conjecture without the Byzantine and unresponsive, and that also had the finite version of the capacity in the conjecture. But the finite version of this has been partially disproven. So in the 2PIR case, so when you have 2 colluding servers, 2 files, and 4 servers, Sun and Jafar designed a scheme that can get a higher rate than this left-hand side expression. But the query scheme is non-linear, so maybe it can still be true for linear schemes. And also I believe that the case 2 files is very special in the sense that there's only one other file that you don't want, and that simplifies things a bit and maybe allows you to do something a bit special. Anyway, we have shown in this recent ITW submission that these asymptotic capacities in conjecture 1 and 3 actually hold for any strongly linear PIR scheme for any number of files. And a small caveat is that we are assuming that all servers respond with equal size responses. One can relax that and look at the expected response size, and then you can improve it a bit for finite number of files. But okay, here just to summarize the different capacities and conjectures. So the black ones are known and the red ones are conjectures. And we have proven the right-hand side red expression in full and the left-hand side red expressions for strongly linear schemes. And what is maybe worth noticing is that on the right-hand side of the table for symmetric PIR, it's kind of easy to combine these different cases to come up with a more complicated case as above, so that part was easy to do. But then on the left-hand side, it seems somehow much more difficult to combine this coding and collusion. They're kind of different in nature in a sense. And what helps in the symmetric case is that you get rid of a bunch of these mutual information expressions because you also have server privacy, so any mutual information between any query and a file that you didn't want should be 0. Or, sorry, responses and the file that you didn't want should be 0. So things cancel out a lot. And so why do we mainly care about the asymptotic case anyway is that the convergence is really fast. So the rate will decay exponentially in the number of files, which is a very big number. So we get, with 5 to 10 files, we are essentially asymptotic already. So the, let's say, non-asymptotic PIR, it's interesting for theoretical purpose, but not so much relevant in practice. Okay, so then what is this strong linearity that I already mentioned a bit? So we say that a scheme is strongly linear if each symbol of the file xi that I want can be obtained as a deterministic linear function over my finite field of the response vector, and it doesn't depend on the randomness used to produce the queries. So this is kind of a very natural and practical feature. If you think of this in an algorithmic sense, then it's very nice that you can always deterministically do your decoding. It doesn't matter which random vector you happen to choose for your queries. Another nice feature is that by doing this strong linearity, we can use a so-called star product scheme, and that gives you a very small field size because you can use Reed-Solomon codes, basically. Also, it allows you to have low sub-packetization level as opposed to these finite capacity achievable schemes that have subpacketization n to the m, so exponential in the number of files. So by doing this strong linearity, you can get a very low subpacketization, which is only dependent on the number of servers, basically. Okay, and I won't really have time to explain you what the star product scheme is if you're not familiar, but just to a little bit outline what kind of scheme it is. So we call star product, or it's also called Schur product or Hadamard product, this kind of component-wise multiplication of two vectors of same length. And for codes, we can define a star product code as the linear span of all such star product vectors, where we take the first vector from the first code and the second vector from the second code. And we have also something resembling the singleton bound, which relates to these dimensions of the different codes. And why we use Fritz-Solomon codes is that they are essentially the only ones that can get to this product singleton bound. And why this bound is relevant to us relates to protecting against collusion and so forth. So we get optimal collusion protection with optimal freight by doing this Fritz-Solomon coding. Okay, so this star product scheme is basically a fully general coded retrieval scheme that protects against any T servers colluding. It's asymptotically capacity achieving at the known points, so where we have either no coding or no collusion. And when we employ them with MDS generalized Fritz-Solomon codes, and it achieves the capacity in these previous conjectures in the asymptotic case. And what was somehow novel in this scheme was that instead of picking these queries from the whole linear space, we also pick the queries from a code. So we pick M queries from a length n code. And then there is some kind of smart interplay, which is exactly a star product as defined on the previous slide, between this storage code C and this query code D. And T in the dimension of the code D refers to the collusion protection. And this scheme happens to be strongly linear, and we have shown in this ITW paper that no strongly linear scheme can be better than this star product scheme with some small caveats. So that's why I've written essentially. So again, if you consider the finite number of file case, then considering this expected download instead of the deterministic all servers respond with all equal size responses, you can improve a little bit on the finite case. But as I said, convergence is very fast, so we mainly anyway care about the asymptotic regime. Okay, and then getting to the results, and this may be now, the expression may not make so much sense to you because I didn't really show you in detail what the scheme is, but we have consider a strongly linear PIR scheme and M files, and we denote by Dij the linear span of the row vectors that can occur as the jth row of my query matrix. So these are basically coming now from linear space, and this is why this is called strongly linear, because this is not usually assumed for PIR schemes. And then I can show by looking at the dimensions of my related star product codes that the rate that I can get is at most this expression. And now for simplicity, if we assume that all the servers respond with equal size responses, then I can simplify it to this expression here. And finally, what the theorem says that, which I now won't be proving to you, but if you take any strongly linear scheme, then you can replace it by our previous star product scheme, and you won't be losing in the PIR rate. So basically, the star product scheme in this, with this assumption that all the servers send you same size responses is optimal. So now if we have a strongly linear PIR scheme, and we know that the star product is an optimal such scheme, we can just look at the rate that we can get with the star product scheme, and it happens to be this one according to our earlier papers. So it is independent of the number of files, and earlier we conjectured that this is the asymptotic capacity, but now with the strong linearity assumption, we have shown that this is actually the rate expression for any number of files. So the capacity of strongly linear PIR is this expression for any number of files. And Zhao Tian has shown in, I think, coded case with no collusion, that again for finite number of files you can get a bit better rates. So you can essentially get to the what you would guess maybe to be the finite version of this expression coming from the geometric series, as in the other cases. then we can get something like that. But again, it gives you something a little bit better when you have, let's say, 10 or so files or less, and then it decays to this asymptotic expression anyway. Okay, so just to conclude quickly, we have proved some capacity conjectures. In full, this very straightforward combination of various symmetric capacities to combine them into one big expression that includes everything. And then proving the strongly linear case for the coded, colluded, and Byzantine unresponsive non-symmetric PIR. And try to demonstrate the importance of strong linearity because it gives you small field size, low subpacketization. It's anyway, let's say, algorithmically very simple because your responses or decoding doesn't depend on the chosen randomness. And what are still open problems is still this general, so what we can now call weakly linear coded colluded PIR capacity. So we don't still know what that is without the strongly linear assumption, but I assume it will be the same one, at least for the asymptotic case. Then parcel privacy, so one can think that these schemes are a bit complex in the sense that if we have a lot of files, then the servers will be XORing or adding up a big number of files on average. So it would be nice to relax on that and figure out what to do. And then also here we assume that the user already knows which file he wants, but of course in general you would first need to figure out what is the interesting file, and then you would have to do something like private keyword search, and there's also not really any very practical schemes for this purpose. Okay, and references, I'll just browse through them on the fly. You can find them in the paper. And thank you very much.
Let's thank the speaker.